last class meeting or lecture meeting for this semester. Couple of housekeeping things. Homework 3 is due tomorrow. I hope all of you are aware of it. It is due through Canvas. Please submit. Please submit as a PDF. Please do not email it to me. There's a good chance that I might miss your submission and then it might not get graded. So please submit through Canvas. Number one. Number two, the take home exam will be posted sometime tomorrow, maybe by evening, so that I would start the clock at midnight. So you will have, I haven't decided fully, but at least 4 days, maybe 4 to 6 days to do the exam. It will be definitely doable in 4 to 6 days. So I don't want to drag it and give it to you like 7 or 8 days, because if I post it tomorrow, Thursday, Friday, Saturday, Sunday, and let's say Monday, due by Monday, it will give me a chance to grade it by Monday evening, and your scores and letter grades will all be done by Tuesday at best. Okay, so it will be posted by tomorrow evening. Number three, your exam 2, the take home version as well as the in-class version grading. I haven't done that yet, but I plan to do that in the next couple of days, and I will have it available on Friday for you to come and pick up in my office. It will also give me a chance to talk to you if there are any questions or concern. So I will be in my office from noon until 4:30 on Friday. You are welcome to just pop by and pick up your exam from me, okay, on Friday. Any questions? Do you have any questions? Clear? Okay. So today the agenda is I'm going to pick and solve problems that illustrate what we discussed in chapter 4 and 5. You can take these questions as very indicative of what you can expect in exam 3. So these are basically the type of problems you will be expected to solve in exam 3, and I'm just trying to give you some practice. Okay. You are also welcome to ask questions related to homework 3. If you want to discuss something, we can talk about it today. Today is your chance to ask me questions and get everything sorted out before your exam kicks in at midnight tomorrow. Okay. Clear? All right. So this is problem 4.1. It talks about a motion given as this: x1 equals alpha 1 x1, x2 equals alpha times x2, and x3 equals alpha times x3, which is essentially if alpha 1, alpha 2, alpha 3 are constants, you would call this uniform stretch. We saw this in the chapter on kinematics. They are time dependent stretches. They are still uniform, but it is time dependent now. And the problem asks you to for this motion, show that the continuity equation is satisfied. Continuity equation, well, you know, is written in terms of the density and the velocity in the spatial coordinate. You need to show that this left-hand side, if you compute, will be equal to 0. That is the question. Okay. So where would you be? What's the first step? What is the first step? You need to show that this left-hand side is 0. So first of all, you need to have expressions for density and velocity for you to plug into this equation. Okay. Right. So how will you get density? So actually equation 4.2 is this one. Rho times divergence of V equal to 0. This is equation 4.2. Let's do the easier thing first. How will we get velocity here? How to compute spatial velocity? How to get spatial velocity? You know this, you did this in the previous chapter. What is spatial velocity? Louder, please.
Deformation rate.
Deformation gradient is not spatial velocity. Deformation gradient, or I think, no, it's not spatial velocity.
Change in spatial position of time.
So change in spatial position over time, or in other words, if you write what I showed you or what I taught you as a method is to write the material velocity is partial x over partial time. You remember this? Once you get the material velocity, use the motion to eliminate the material coordinates from that. So what is this? This is going to be at constant for a constant particle. Do you remember this definition? Particle velocity is the rate of change of position for a fixed particle or for a particle. This would be alpha 1 dashed of t x1, alpha 2 dashed of t x2, alpha 3 dashed of t x3. Take a look and let me know if that makes sense to you. All I'm doing is differentiating x with respect to time, treating material x like a constant. So this will just be the derivative of this time dependent function alpha 1, alpha 2, alpha 3. Are you with me? Is that okay? So this is particle velocity, okay? This is material or particle velocity. Material or particle velocity. How to get or how to go from material velocity to spatial velocity? This is in terms of the material coordinate, and this is in terms of the spatial coordinate. If x equal to p of x comma t, this is what you call the motion, then you can rewrite this as x equal to p inverse of x comma t, which is like writing x1, x2, x3 is equal to x1 divided by alpha 1 of t, x2 divided by alpha 2 of t, x3 divided by alpha 3 of t. Assuming alpha 1, alpha 2 are not 0. So wherever you get this x1, replace it with x1 divided by alpha 1. Wherever you get x2, replace it with x2 divided by alpha 2 and so on. With me so far? So V is of V of x comma t is obtained as V tilde of x in terms of spatial x comma t and time. So that would be alpha 1 dash of t divided by alpha 1 of t multiplied by x1, x2 alpha 2 dash of t divided by alpha 2, x3 alpha 3 dash of t divided by alpha 3 of t. You're going to take a picture? So I am also recording, and also I posted up to the last lecture on my YouTube channel, and I did update the syllabus also. I know some of you are watching because within posting there were like 7 or 8 views and even one like. Whoever that person is, thank you. So I'm still waiting to be a YouTube star, but hasn't happened yet. They watch only like a couple of minutes. Anyhow, are we clear up to here? Velocity in terms of x1, x2, and x3 or spatial coordinates. Now you want to compute what is divergence of v. What is divergence of v? Divergence of v is partial vi over partial xi, which is alpha 1 dash of t divided by alpha 1 of t plus alpha 2 dash of t divided by alpha 2 of t plus alpha 3 dash of t divided by alpha 3 of t. Is it okay? I just took this velocity in terms of the spatial coordinate and did dot product, or sorry, divergence, which is partial vi over partial xi. So if I put this expression in here, I have partial rho over partial t plus rho times wherever divergence of v is, I'll apply this alpha 1 dash of t
On the left side, the equal sign.
Yeah, we are just computing this part. We have to show this is equal to 0.
Was on the left side of equal LHS.
LHS.
Is that
That is, I'm just saying, okay,
left hand side?
left hand side. Yeah. So if I write this is equal to density times 1 over rho, partial rho over partial t, plus I can write 1 over alpha 1, or actually just to keep it short, I'll write 1 over rho dot, plus 1 over alpha 1 dot, plus 1 over alpha 2, or rho dot divided by rho, plus alpha 1 dot divided by alpha 1, plus alpha 2 dot divided by alpha 2, plus alpha 3 dot divided by alpha 3. You still need to show that this is equal to 0. It's coming up to something. How do we show it to be 0? That's the question. Just writing it this way to see if it will give us any clue. What shall we do next? The problem statement also one more part or one more statement. The mass density field in the reference configuration is rho naught of x. So you're told rho naught of x is equal to rho of x comma t times j. So you have to treat, okay, before I say the answer, any thoughts? What's the next step? This is the problem in the exam. You have come up to here, you have written an expression that involves rho and alpha 1, alpha 2, alpha 3. And then you're also told the reference density, that is the density of that material or particle in the reference configuration is rho naught. So treat rho naught like a constant. And you know that rho naught should scale as rho times j. What is j? Louder, please.
Jacobian.
Jacobian, which is determinant of f. Determinant of f. That is determinant of the deformation tensor, which you know now is partial xi over partial xj, ei, ej. Okay. So here's what you need to do. You can treat alpha 1, alpha 2, alpha 3 and their derivatives as though they are known values or known functions because they are given as part of the problem. So you have to treat them like they are known somehow. You need an expression for rho without which you can't show this to be anything. From this expression or from this mass balance, you can write rho of x comma t is rho naught, a constant, divided by j. And what is j a function of? J is a function of x and x. Okay. So the question you need to figure out is if you compute rho and rho dot, or if you just substitute for rho, you can go back to this step here. You can, if you just substitute for rho over here and here in terms of this j, will it all cancel out? That's the question. Will it all add up to 0 if you use the expression for rho and substitute it here? Can you first obtain j? Can you get j? Can you get f? You can, right? F is pretty easy actually. F is, what is f?
Alpha 1 t.
Alpha 1 t 0 0.
Alpha 2 t 0 0 alpha.
Okay, so that's easy, which implies j is alpha 1, alpha 2, alpha 3. We're getting somewhere. So this is like saying rho, you write rho naught is equal to rho times j or rho times alpha 1t, alpha 2t, alpha 3t. Keep remembering that this is a constant. That is the product of instantaneous density multiplied by alpha 1, alpha 2, alpha 3 is a constant. So wherever this appears, I am allowed to write it as rho times d over dt of rho naught. Yes, no? What is the derivative of a constant? 0, which is rho times 0 or just 0, which is our right hand side. Are you able to follow?
It's just the only thing is I don't understand how you new to use like the Jacob new, just out of.
It's given in the problem. Okay, this is given in the problem. If you look at your text, problem 4.1, show that the continuity equation 4.2 is identically satisfied for any deformation of the form x1, x2, and x3, where alpha I of t are differentiable scalar functions of time. The mass density in the reference field, the mass density field in the reference configuration is rho naught of material x. That's what the problem statement reads. That is, they just say the mass density is rho naught of x. Now your question is, how did I know that I should apply it with this? I got your question. Anybody wants to answer that before I give my view? Anybody wants to tell us why or how to pick out this relation and use it to solve this problem? Okay, let's work towards the answer. What is this equation? This is called continuity equation or mass conservation equation in spatial form. Okay, what does this equation represent? It represents the relationship between velocity and density at every point in the material. You're with me? What is this equation? This is saying the density in the reference configuration for a particle. Think about my hammer example. I take a blob. At that point, at that time, I define it as my particle. Every point on that particle has a density. We'll call that density as rho naught. I'm going to write this out because this is something that could be useful for you. And I am repeating some of the things that I already said. Consider a blob of material. Blob meaning irregular shape. Okay. Before any hammering or shock loading, we will call the shape as the reference configuration. So this blob represents the particle which we will denote as material X. This X is spread over a certain spatial extent, and x of x comma t represents the material particle. This extent. So any point on here as a position x, and the instantaneous position, and at the instantaneous position, the collection of all those positions forms the particle. Okay. At time 0, that is before the deformation starts, every point will have a certain density, right? Every point has a density which we will call rho naught. Every point has a density value, and this rho naught is for that particle, and that particle itself is defined as a bunch of points. With me? Okay. So this equation that I used here, rho naught of x is equal to rho of x comma t times j represents the relation between density at a point x at a later time t and the reference density rho naught. That is, it's like saying at every point on this block, no matter what its current shape or current configuration is, this relationship is satisfied. The local density always is the reference density divided by j, or the local density multiplied by j is a constant or is equal to the original reference density. The simplest way you can think about it is you take like a sphere, uniform sphere. If you squeeze it axially, like squeeze it along the vertical plane, it's going to bulge on the sides. Like take an egg, you squeeze it from the top, it's going to bulge on the sides. At every point, if you try to squeeze in more material, you cannot indefinitely squeeze it. It has to be connected back to the original way you apply the deformation, and that is what J represents. So while this equation is applicable at every point, this equation is applicable at every point. This equation is also applicable at every point, provided that point is part of a particle. You can't apply this point in space where there is no material. This is applicable wherever there is material. If you had a material at that point, you squeeze it, the material has to compress or it has to expand. It cannot just vanish. That's what this equation does. So it's basically the same principle, mass conservation in spatial form, mass conservation in material form, which we use to establish that density at any given point cannot be changing without a constraint. It is constrained by the reference density. Okay, so if I write that rho times j is equal to rho naught, that's what I do here. Wherever rho times j appears, wherever rho alpha 1, alpha 2, alpha 3 appears, which is nothing but j, I am replacing it with rho naught, which gives me 0. So the answer to your question is you need to know the principle of conservation both in spatial form as well as in material form. You need to know the principle of momentum conservation both in spatial form as well as in material form. Maybe not so much the momentum conservation, but mass conservation, definitely you need to know this equation. Good thing that we discussed this example today, because something like this is bound to come in the exam. Because there are only like few topics that I can ask you. This is definitely coming. Okay. So the same problem has your deformation mapping. It makes you compute velocity. It makes you convert material velocity to spatial velocity, and then use that in the operator to work out here. And then you have to use the mass conservation in material or particle form to close the loop. Like one stop, test everything. Okay. Not only that, although the exam 3 is not comprehensive, that is, I'm not going to ask you questions on prior topics, it still involves prior topics indirectly. Okay. So the 4 or 5 days is basically for this inspiration to strike. And if I ask that to strike in 80 minutes, it's sometimes difficult. But 4 days, 5 days, I hope it will happen. Let's do problem 4.5, unless anybody else has any question they want me to try. Problem 4.5. You have a question?
Yeah.
Yeah. Okay. All right. Thank you. We'll do that. So let me read the problem. The rectangular Cartesian components of a particular Cauchy stress tensor are given by sigma equal to a matrix, 3 by 3 matrix. Determine the unit normal of a plane parallel to the x-axis, that is n3 equal to 0, on which the traction vector is tangential to the plane. What are the constraints on A and B necessary to ensure a solution? First of all, this is highly mathematical. I would suggest you always draw a sketch and label the three axes to determine to first figure out what is being asked. Okay. And then the second part is, if A, B, C, D, E are functions of x1 and x2, find the most general forms of these functions that satisfy stress equilibrium in equation 4.27 in the absence of body forces. Shall we do the first part first before we get to the second one? Like, you may not have a question, but others may want it. Okay. So if you have your book, please refer to problem 4.4. So sigma is given by A 0 B 0 B D E C. All right. Determine the unit normal of a plane parallel to the x3 axis. So if I draw x1, x2, x3, a plane parallel to the x3 axis, how will it look like? So this is x3 axis. Something parallel to the x3 axis. So you can write n cap equals to n1, n2, 0. And of course, n1 squared plus n2 squared should be equal to 1. So make it a unit normal vector. Determine the unit normal of a plane parallel to the x3 axis on which the traction vector is tangential to the plane. Traction vector is sigma dot n. What they are saying is traction vector is tangential to the plane. Meaning the referring to this plane. So how will you convert this statement? So this is the definition of traction vector. So this is not anything new. This is basically the definition of how do you get the force on a surface by taking the stress multiplied by the normal vector. Please, this should also include area. No, it's correct. It's correct. Yeah, traction vector is equal to sigma dot n. Please convert this statement into a math equation for me. What does it mean to say tangential to the plane? If I have a vector A and I have another vector, let's say I call it B. If I want to say B is tangential to A, what is the relationship between B and B? If I say normal, it's easy. If I say B is normal to A, immediately you will say B dot A is 0. That's not what we want. We want to write B is some lambda times A. Isn't that what you say tangential? Yes, no? Temuri? Yeah. Yes?
Yes.
Okay. So when you say traction vector is tangential to the plane, this basically means T is some constant times N. So T, which is equal to sigma dot N, is also T is equal to alpha times N. You know this story. What is the ending? So if you have a matrix, or if you have a tensor, if you write A dot X is lambda times X, what is lambda? Eigenvalue. So if you write sigma dot N is also some alpha times N, then alpha has to be the eigenvalue of sigma. You can do it both ways. You can first calculate what are the eigenvalues of sigma and show that this will automatically be satisfied. Or you can evaluate both sides because you know what is n in terms of n1 and n2, and then try to get constraints on alpha. Either of them are fine. Okay, can you try this? That is, can you actually try evaluating sigma dot n? You already completed the first part, right? Okay. Can you tell what is sigma dot n?
AN1, BN2.
So AN1 plus AN1,
BN2.
BN2,
BN1.
DN1,
EN2.
and 2 is equal to some alpha times N1, N2, 0. So first relation says AN1 is equal to alpha N1. Second relation says BN1 equal to alpha N2. Third relation says DN1 plus EN2 is equal to 0. What is the next step?
So I did the wrong thing. I equaled the other side to 0. So that was the problem I had. So
Okay, so let's see what we can do here. So what does the problem read? Problem reads, what are the constraints on A and B necessary to ensure a solution? That's the question. I'll write it here. What are the constraints on A and B necessary for a solution? What are the constraints on A and B necessary for a solution? If you consider if A equals to B, what happens? Then you have A and 1 equals alpha and 1 and A and 2 equals alpha and 2. If alpha is equal to A, then this is 0, N1 can be arbitrary. This is 0, N2 can be arbitrary. If alpha equals A, N1 is const C1, N2 is C2. Both are arbitrary. If both are arbitrary, what does it mean for necessary for a solution? If both N1 and N2 can be any values, what does that mean? Means there are infinitely many choices. You can choose N1 to be anything, N2 to be anything. There is no unique solution. So this means no unique solution. This is not an outcome you want because it doesn't help you get any clarity. You are trying to model an engineering problem. What's the purpose of getting infinite solutions? Nothing. It won't help you make a decision or understand something. You need unique solutions. So if we are seeking unique solutions, what happens if we assume A is not equal to B? See, look at the third equation. This is like writing N2 is equal to minus N1 D over E. N2 is minus N1 B over E. So if I take N1 times alpha minus A equal to 0, and then if I write N2 times alpha minus B equal to 0, whereas N2 I will write minus N1 D over E alpha minus B equal to 0. Either N1 can be 0 or alpha equal to B. We're not considering D and E, we'll assume they are non-zero. So this implies either N1 is 0 or alpha equals B. If N1 is 0, what is N2? 0. It means you just get 0, 0, 0. That's trivial solution, again useless. It's like basically saying the plane 0, 0, 0, if you multiply it with anything, you will identically get the same thing. This is not a solution. So this is useless, or this is not the one we are seeking. A is not equal to B, but B is equal to alpha. That is the case, then N1 can be anything. N1 is, this implies N1 is arbitrary. But N2 is not arbitrary. What is N2? N2 is always minus B over E times N1, which implies N2 is minus B over E times C1. So what is your vector then? Your vector is n cap is n1, which we'll call as c1 times 1 minus d over e 0. Since c1 is arbitrary, I mean I have to divide this by the magnitude, right? C1 times 1 plus d squared over e squared. So this is your vector which will satisfy this relation, and for that to be satisfied, the answer is, first of all, a cannot be equal to b. Second, b is equal to alpha, or in other words, sigma dot n is equal to b n. You are taking a picture means you agree with this. I mean, logically, I'm asking, does this make sense to you? So when you are taking the take-home exam, I would even suggest keeping a textbook of vector algebra next to you, because what I've used here most of the time is basic concepts of vector algebra. Like what does it mean to be tangential, or what is eigenvalue or eigenvector? Basic concepts. Okay, keep your, if you have taken engineering mathematics, crazy textbook with you, you should be okay. Everybody is in agreement. You feel this is making sense to you, even though you may not have done it this way or may not have thought of it, but at least after seeing it, do you agree? Now let's go to part 2. If a, b, c, d, e are functions of x1 and x2, find the most general forms of these functions that satisfy stress equilibrium in equation 4.27 in the absence of body force. So what is equation 4.27? Equation 4.27, it basically comes from here. Rho v dt plus divergence of rho vv equal to divergence of sigma plus rho times b. This is the momentum conservation equation in general form, which includes motion, which includes the velocity vector. If you are at equilibrium, the entire left side is 0 because there is no motion, everything is in balance. So there is no acceleration. So we say left side is 0 for, actually, let me erase this. Oh, can I erase this? So momentum conservation, momentum equation in spatial form. This is given by equation 4.26. Equation 4.26, which is my favorite form because it is easy to remember and it's called the conservative form. Divergence of rho Vv equal to divergence of the stress tensor plus any body force. Equilibrium means the acceleration rho a, which is written as rho v over t plus divergence of rho vv. This term is 0. There is no acceleration. That's what equilibrium means. You are in balance. So this whole left side drops out. And then we are also told no body force, which means rho times B is 0. So you get divergence of stress tensor equal to 0. What is this in index notation? This is like writing partial over partial xj ej, or I'll write xk ek dot sigma ij ei ej equal to 0, or this is partial over partial sigma ij partial sigma xi equal to 0 times ej equal to 0. This is the vector. Do you see that? This is a vector. I is a repeating index, j is a non-repeating index, making this a component. So this is basically like writing three components. Partial a over partial x1 plus partial d over partial x3, and then partial b over partial x2 plus partial e over partial x3, and then partial b over partial x1 plus partial e over partial x2 plus partial c over partial x3 equal to 0. We are also told one more little factoid, which is a, b, c, d, e are functions of x1 and x2. It doesn't say explicitly that it is a function of x3. So this term is just 0. So if this vector is 0, partial a over partial x1 is 0. What does that imply? A is equal to function of x2 only, because it's already not a function of x3. And then partial b over partial x2 is equal to 0 implies b is equal to b of x1 only. And then partial d over x1 plus partial e over x2 equal to 0. What can you get from this? I guess we can't go any further. This is it. That is, the constraints are a is a function of x2, b is a function of x1, and the derivatives of d and e must satisfy this relationship. Okay. So yeah. So the learning is, first you should be aware of what is momentum equation in general, what does equilibrium mean, and what is stress, I mean, essentially once you write this equation, then the remaining is just the uh, things you learned in the previous 2 units. So getting to here is actually the big deal. Okay, so converting the English language statement into a mathematical equation, that is most of the work. If there are any questions, I can answer. Otherwise, I want to do problem 4.5, which is one more example we could try. Was everyone here when I announced about picking up your exams, graded exams on Friday? Problem 4.5. A rectangular body occupies the region between minus a and plus a and minus b and plus b in the deformed configuration. The components of the Cauchy stress tensor in the body are given by sigma is given as a matrix. Show that sigma satisfies the linear momentum equation in the static case with no body force. So sigma is given this problem 4.5. Sigma is given as C over A squared minus x1 squared minus x2 squared, or minus of x1 squared minus x2 squared, 2x1 x2 0, and then 2x1 x2 x1 squared minus x2 squared 0 0 0. So this is Cauchy stress tensor in spatial form, that is, it's in terms of x, where a, b, c are positive constants and b is greater than a, where a, b greater than a and c are all positive. Number one, show that sigma satisfies the balance of linear momentum. So balance of linear momentum starts with partial rho v t plus del dot rho v equals sigma, I mean del dot sigma plus rho times v. They tell us static case. What does static means? Static means there is no motion. That's what static means, right? And then no body force, which means B is 0. So both of these lead to del dot sigma is equal to 0, which is like writing partial sigma ij divided by xi equal to 0, multiplied by ej equal to 0. Same thing that we did last time, except we have to do this for this stress tensor, which is like writing minus 2x1 plus 2x1 plus 0, 2x2 minus 2x2 plus 0, and then 0, which is nothing but 0, 0, 0. So it's proved. Okay. Determine the traction, that is part 2 I'm reading. Determine the traction that must be applied to the 6 faces of the body in order for the body to be in equilibrium. That is, remember, it is told the body is a rectangle in the deformed configuration. And that rectangle is given to be something like minus a to plus a in x1 direction, minus a to plus a in x2 direction, and minus b to plus b in x3 direction. So it's like drawing something like this. So can you pick any one face and what will you define it by? You can write x3 equal to b is one of the faces. I'm going to ask what force should I apply on the face x3 equal to b for this body to be in equilibrium. Not just this face, there is also x3 equal to minus b. And then there is x1 equal to plus minus a, and then x2 equal to plus minus a. 6 faces. See, it's a cube, runs from minus a to plus a. So if we say x1 equal to minus a, that defines the face. Same with x1 equals plus a, or x1 equals plus a. So x2 equals a and x2 equals minus a, x3 equals b, x3 equals minus b. So what constant force should you apply on each direction or each face so that del dot sigma plus the force that you apply add up to 0? The question making sense to you? This force is basically 6 vectors, one for each face, that you need to apply for this body to be in equilibrium. That is, you shouldn't start here. That is, you shouldn't write this here. What we are asking you to figure out is, starting from here, 0 equals del dot sigma plus the force on each face, where I equals 1 to 6. I'm actually going to give you 5 to 10 minutes to do this because we have been trying and I've been people have been quiet. So I want you to try. I can walk around and talk to you. So I'm a little confused here because if part one establishes that the body is in equilibrium without any applying body force, if you apply symmetric force, that is, if you take your cuboid, you apply equal and opposite force on these two faces, equal and opposite on these two faces, equal and opposite on these two faces. You really don't need those forces because you're already in equilibrium. Okay, so either I am misreading the question, or the question has something more to it than just this. You know what? Let's not waste time on this. Go to part 3. That is the more interesting question. Calculate the traction distribution on the sphere x1 squared plus x2 squared plus x3 squared equal to a squared. Yeah.
A squared.
That's multiplied with every number. It won't matter there. You can write it here, and it won't matter. If it had been for only one of those, maybe. Yeah. All right. Calculate the traction distribution on the sphere x1 squared plus x2 squared plus x3 squared equal to a squared. Okay. First, I want you to explain to me, what do you understand by traction distribution? You have a system. You are told the stress at every point is given by this function. Okay. If you put a planar area, depending on what the normal vector is, what is going to be the traction? Traction is always sigma dot n. So if I put a planar area at some orientation, whatever that orientation is will determine the traction. Okay. If you take a sphere which is centered at 0, 0, 0, so that the equation of the sphere becomes x1 squared plus x2 squared plus x3 squared equal to a squared. What is the normal vector for the surface of a sphere? At any given point, it's the line joining the center with the radius. You can write this as ER theta. ER. Right? So how will you calculate the traction distribution? That is, you have to calculate what is the distribution of force on the surface of this sphere. That's what traction distribution means. The traction distribution over that surface. How will you do that? It again goes back to knowing vector algebra. It's not even like a real physics problem. It's more like a mathematics. Okay. What is the normal vector at any point on the sphere? N cap on the sphere is just ER cap, but you need to express ER in terms of E1, E2, E3. Can you think how you would do that? This is something we saw in the very first unit. Spherical to Cartesian, Cartesian to spherical. So ER is A sin theta cos phi E1 plus A sin theta sin phi E2 plus A cos theta E3. How do I know this? I'm just basically referring to chapter 2. You'll have 5 days to do this. Can you go to chapter 2 and actually find this? Please try now, those who have your text with you. turn the pages, find this, and tell me if this is correct. Have you found NC?
Yeah.
Page 63, equation 2.102. Page 63, equation 2.102. Page 63, equation 2.102. The only thing I have added here is multiplied by A. Can you explain why? Radius of the circle. Like I have a sphere whose radius is A. If I want to denote any point, I have to multiply by the radius. If it's a unit circle, we will just write A is equal to, or a unit sphere. Okay. So once you have this to write n in terms of E1, E2, and E3, that is your basis in which this tensor is expressed. You still have one problem. You have introduced this theta phi. How will you eliminate theta and phi? How will you express theta phi in terms of x or x1, x2, x3? Theta phi in terms of x1, x2, x3. Same page 63, equation 2.101. You are given x1 squared plus x2 squared plus x3 squared equal to a squared. That is the relation for the radius. And then you have theta is equal to cos theta is equal to x3 divided by a, sin theta is, sorry, not sin theta, sin phi. Tan or tangent of phi is x2 divided by x1. So you can write x3 is equal to cosine inverse of I'm sorry, theta is equal to cosine inverse of x3 over a, and then phi equals tangent inverse of x2 over x1. The point is theta, phi are known functions of x1, x2, x. Okay. So now you want to get traction distribution over the surface of the sphere would be T of x is equal to sigma dot n. N is not a constant, n is not a fixed direction, n is also a function of x. So you can write this is sigma of x dot n cap of x. What is n cap? So what is sigma? Sigma is that matrix you are already given. Dot. What is n cap? N cap is this one here. A sine theta cosine phi. A sine theta sine phi and A cosine theta. I won't do the matrix multiplication, but this is in terms of x. This is in terms of x. So I assume you can take it home from here. The main concepts we are learning is if you have a surface has a well-defined n, like a normal vector, which for the sphere is really simple to state, it's just the radial vector. And if you want the traction distribution, that is the stress tensor dot the vector all over the surface. Okay. If so for a sphere, it's easy to state what n is. Okay. What about ellipsoid? Ellipsoid is x1 squared over a squared plus x2 squared over b squared plus x3 squared over c squared equal to 1. This is the ellipsoid. Or in general, you might have a function f of x1, x2, x3, some kind of arbitrary surface. How will you get n cap? That is, how will you get the normal vector for any surface, not just sphere, which is easy, for any surface. This is again a vector algebra thing. N cap is gradient of f divided by magnitude of f. This is like a trick that I'm telling you, because tomorrow in the exam, maybe a sphere won't come, maybe an ellipsoid might be given, or some other surface might be given. Here's your way to calculate the normal vector for any surface and then apply this. Or at least if you see this problem in the exam, go back, watch the video again, and I'm telling you now the solution. Or solution process, not the solution. Now I know what will be the most watched segment in the video. Let me make sure this came on camera. I wrote it too far away. Yep, that's good. Okay, so I'll stop here. Again, homework 3 due tomorrow by 4 p.m. on Canvas. Please don't email me, put it on Canvas. I will post the exam by tomorrow midnight. And most likely you will get at least 4 days, most likely 4 or 5 days to do the exam. And if it's due by Monday, I hope to have your grading done and posted by Tuesday or Wednesday. Okay. Again, no paper submission, no email submission, only Canvas for exam 3. Regarding exam 2, on Friday between 12 to 4, I will be in my office. Feel free to come and pick up your graded exam 2 and we can chat about whatever questions you may have related to exam 2, related to exam 3. I won't obviously tell you the answer, but I will at least help you little bit understand what's going on, interpret the question for you. That's all. I won't give you any more hints, do this, try that, look here, nothing. I'll help you interpret the question if you want. Okay, 12 to 4, I'll be in my office. I'll put all of this in an email and send it tonight. Thank you. Thank you for the great semester. And please do the course evaluations later. Okay, yeah.
This 4 o'clock pretty strict for the homework tomorrow, or is that?
Sure, take until midnight for all of you.